Earth's atmosphere acts as an immense integrating detector. Every long-lived chemical emitted on the surface eventually mixes into this global volume, leaving a measurable trace. For international regulators enforcing the Montreal Protocol, this physical reality is highly useful. Instead of inspecting every factory on Earth, they use top-down mass balance inversions to mathematically infer how much of a chemical is being produced, based entirely on its concentration in the sky. This monitoring is critical for legacy ozone-depleting substances, particularly the heavily manufactured halocarbons, CFC-11 and CFC-12. Both were historically produced at massive industrial scales. Both are completely controlled today, and both persist in the atmosphere for decades. To police global compliance, scientists track these chemicals using a simplified global burden equation. Atmospheric mass change equals surface emissions minus atmospheric loss minus net ocean uptake. Isolating the emissions term reveals exactly how modelers solve for factory output. It relies entirely on accurately subtracting the chemical destruction in the atmosphere and the ocean sink. But this architecture contains a structural blind spot. It treats the ocean's capacity to absorb CFCs and the atmosphere's capacity to destroy them as stable, static baselines. The operational framework of the Montreal Protocol has a strict default assumption built on this static math. If the expected atmospheric decay curve of a controlled chemical noticeably flattens out, that stabilization is treated as evidence of illicit new factory emissions. But the ocean sink is not static. The real ocean is undergoing rapid warming, creeping acidification, and increasing freshwater stratification. Top-down inference uses the entire planet as a variable. Any unmodeled natural process that leaves more chemical mass in the atmosphere than expected risks being mathematically misassigned as an illegal human action. This is a thermodynamic attribution error. If inverse models fail to explicitly resolve the changing physical state of the water, they automatically convert an environmental gas rejection into phantom industrial factories. To understand exactly how the math fails, we have to look closely at the mechanics of the ocean boundary layer. True air-sea flux is not dictated by a static holding capacity. The physical transfer relies on Henry's law and its solubility coefficient, K0. This equation defines ocean flux through the pressure gradient. Notice that the solubility coefficient sits squarely in the denominator. The Warner-Weiss coefficients for CFCs dictate that this solubility is steep and negatively dependent on water temperature. A warmer body of water physically holds less dissolved gas. As the mixed layer of the ocean warms, that physical solubility coefficient shrinks rapidly. Because it sits in the denominator, shrinking it forces the implied oceanside partial pressure to spike upward. This narrows the disequilibrium gap, collapsing the driving gradient and physically stalling the downward transfer of gas. The 2023 to 2024 El Niño marine heatwave provided a massive real-time stress test of this exact thermodynamic mechanism, breaking standard static models. This map details sea surface temperature anomalies during the summer of 2023. By August, the modeled global sea surface temperature anomaly reached a positive 1.0228 degrees Celsius. Crossing this 1 degree threshold triggered an immediate cascading effect. It caused a 16.51% total collapse in the global ocean's ability to draw down CFC-11. In strict mass balance terms, this thermal uptake resistance generated a massive atmospheric mass shift. It left a 0.067 gigagram per year unabsorbed residual floating in the lower troposphere. To a top-down mass balance model lacking dynamic temperature coupling, that unabsorbed thermal residual looks mathematically identical to a sudden illicit factory emission appearing out of nowhere. This misattribution extends beyond the ocean sink. We must also examine the atmospheric loss term, the primary variable used to track global methane emissions. Because inversions measure the total methane burden directly from atmospheric data, they deduce surface emissions algebraically by subtracting modeled chemical destruction. To solve that equation, they prescribe exact baselines of the hydroxyl radical, or OH, the primary chemical sink that clears methane from the sky. Relying on a fixed OH baseline creates a systemic vulnerability. Extreme weather initiates a process called the marine radical pump, which rapidly reorganizes atmospheric chemistry and heavily distorts those prescribed static baselines. It starts with a thermodynamic trigger. Applying a positive 3 degrees Celsius marine heat wave decreases the water's solubility coefficient by 15.9%. The warmer ocean physically loses its capacity to hold dissolved halocarbons, forcing biologically produced bromoform toward the surface. We couple that heat wave with the kinematic forcing of a storm. Increasing surface wind speeds to 12 meters per second forcefully ventilates the saturated ocean. This violently strips the bromoform into the lower atmosphere, amplifying the source rate by 583.8. A top-down inversion assimilating satellite data observes this rapid chemical scrubbing, but processes it against a static baseline that assumes the chemical sink hasn't changed. To balance the equation, the model concludes that local farms, landfills, and oil facilities must have simultaneously reduced their output, fabricating false compliance on land. A third critical assumption in standard inversions is that surface gas transfer velocity is driven purely by wind speed over an unstratified, well-mixed water column. In reality, heavy rain and ice melt alter the sea surface, creating sharp near-surface salinity gradients known as haline capping stratification. These distinct freshwater gradients generate positive buoyancy fluxes that physically stabilize the upper water column. The stability mechanically dampens the turbulent kinetic energy dissipation required to push gas across the air-sea interface. As the turbulent suppression factor decays to zero, it restricts surface renewal, functionally acting as a physical lid on the ocean. Applying standard wind speed parameters over a highly stratified ocean exposes a profound model failure state. It forces the system to assume the water is actively absorbing trace gases long after the physical sink has actually closed. Ignoring this physical cap completely blinds treaty enforcers. The algorithm mathematically misallocates the surviving airborne mass, logging it as a sudden anomalous spike in land-based human emissions. To measure the weight of these variables, researchers ran a triple counterfactual numerical integration experiment, isolating the exact systematic error injected into standard inversion readings for CFCs and methane. This chart tracks the resulting discrepancies. Omitting the haline gradient forces the static model to overstate oceanic uptake. Because the ocean's sink isn't actually pulling that weight, the atmospheric mass stays airborne, and the algorithm automatically misallocates that surviving gas as an 11.4% error in anomalous CFC-11 emissions. The second constraint hits the methane ledger. Failing to dynamically couple ocean acidification kinetics and biological volatile surges artificially shortens the atmospheric methane lifetime proxy by 4.2%. The central enforcement problem today is one of proportionality. As global regulatory compliance improves, true anthropogenic emissions edge closer to absolute zero. In this highly tightened regulatory regime, interpreting sub-gigagram deviations becomes the primary operational task of international monitoring bodies. As enforcement thresholds tighten, these single-digit percentage errors in methane lifetime or CFC uptake evolve. They are no longer minor mathematical artifacts. They are critical, policy-altering false positives. Global monitoring architectures must now abandon static boundary assumptions. They need to transition to dynamically coupled biogeochemical inversions. This requires integrating the stratified marine feedback engine. This framework uses a 17-state implicit solver suite that explicitly links ocean acidification kinetics, biological volatile production, and haline stratification. Integrating these dynamic variables establishes a new mathematical baseline for accurate enforcement. Reported emissions must equal the raw atmospheric inference, minus the explicitly calculated ocean sink bias. That new ocean sink bias variable mathematically filters out environmental noise, clearly separating the natural physics of the climate from actual human-driven compliance shifts on land. To secure the credibility of international law under the Montreal Protocol, formal residual attribution rules must be established. The atmospheric science community must first isolate and subtract the thermodynamic physics of a warming Earth before attempting to police human industrial activity.